Welcome to Unit 2 on fundamental data structures. This will be the first unit where we really dive into the computer science topics and we leave the mathematical preliminaries behind us, finally. It will be a recap unit for all of you who have an undergraduate degree in computer science. You will have seen most of what I present, and I also will go over this at a fairly rough pace. So there's a lot of extra material on the website, in particular, really well done lecture videos, professionally studio recorded ones. They're not for free, but they're really worthwhile investing time and a little money into them if you want to understand these topics in more detail. For what we need in this class and for your course, everything will be covered in the lecture. But again, if you feel you want to be a full-fledged computer scientist, you won't get around knowing the basics of these data structures. And my lectures today and next week will probably only scratch the surface. If you want to go deeper, you're encouraged to check out the website. But that said, let's see what I can do for you today. We'll talk about the very basic data structures, and I will probably start with a little bit of what linked lists are. Maybe just the term was not what you knew. We'll talk about resizable arrays and as a building block for other data structures. And finally, the two big classic data structures in computer science that build on these very elementary ones: priority queues and binary search trees. First, very basic data structures, stacks and queues that you might have seen, or maybe even the terms are intuitive enough to make out what they mean. But I will use these to also introduce the concept of abstract data types, which is an important conception, an important concept in computer science that people found very useful. So let's look at what that is. The contrast is to be drawn between abstract data types on the one side and concrete data structures on the other side. And if you've learned programming in Java, then it will help you to think about abstract data types as something like the interfaces in Java, where you specify the operations of the methods, but you don't provide any implementation. And data structures are the concrete classes that implement a certain interface. Of course, you can have classes that don't implement any interfaces, but what I really mean is you have an abstract data type on the one side, an interface, and then a class that implements it. This analogy is useful, but it's not a complete and true representation of what abstract data types are, so it's helpful to keep the two separate. Oh, I see. Someone pointed out that the question I asked only allowed one answer, and that's, of course, nonsense. So let me maybe open that one again. And let's reset the results and just do that exercise again. Thanks for pointing that out. It's a weird interface in Slido. If you don't say limit options, then it's just one. Okay, so we get a different turnout. I'll briefly show the turnout in a minute. The distinction between abstract data types and data structures is fundamental, so I want to cover that part either way. So Java interfaces are what you can think of, but an abstract data type has to have a little bit more than just a method name. It has to list the supported operations, but it should be precise in specifying what exactly should happen. So you want a little bit of a clear description. It can be natural language as usual. If we're doing this for humans, it can also be a little more formal than that. What it does not specify is how to implement the operations. and it also doesn't say how to store data that is associated with a certain data structure. And on the other side, data structures do exactly that. They tell you exactly how the data is represented. They tell you exactly how the operations are implemented. And it has, because of that, the algorithms have concrete cost in time and space. Using the analysis methods from the last unit, you have an idea how to work out these costs. So this is what you can really implement in a program and what you can run. An abstract data type is just a shallow interface where you can't really use this to run a program. You always need an implementation. You can argue why it makes sense to separate the two. I can think of a couple of reasons. From a practical perspective, it's helpful if you can swap out implementations. That's what people in Java do a lot. You can say, I have a list of objects, and then you can specify it's a linked list or an array list. That makes code more reusable, both on the client side that uses a data structure or an abstract data type then, and on the implementation side of a specific abstract data type. You can create linked lists once and use them wherever you need them. It's also helpful because it often allows better abstractions, and I think this is it's underappreciated how much that helps to build programs and to understand a task at hand, a computational problem. And lastly, it's also the way to approach lower bounds. If you can isolate the functionality of a certain task to an abstract data type, you can talk about what are the best possible implementations for this abstract data type. That's something that's hard to do if you always mix your data structure with client code. Okay, with that, let me show the results from the opening poll again. People still know arrays, but half of you know linked lists. That's reassuring. And many of you have seen binary search trees. A quarter or so has seen binary heaps. And okay, good. So I was figuring some of you must have seen the more advanced data structures as well. Good. So as I said, I won't talk about hash tables, and I won't talk about these two, but we'll talk about the rest and do that somewhat briefly. Okay, let me tick off these two. As a last point, I want to mention that despite all these positive aspects of having the separation between abstract data types, a clean interface, and then implementing it, sometimes an interface doesn't really help much. And like in this example, right, you see the hose coming out, and then it looks like it's a nice fountain, but it's really just a stone with a pipe in it. Sometimes this separation and this rigid abstraction can also be harmful, and it's occasionally useful to break it open. And that's why I think it's so vital that you don't only know the abstract data types, and you know that there's implementations of binary search trees and all the like in programming libraries so that you can use them. It's also vital for computer scientists to know what's inside the black box so that in some cases you can break it open and exploit that fact and get to a better solution. With that, I want to see again a little bit how well these terms are known to you. Now, before I start that, let me double check that you can, that was the wrong one, this one, that you can actually answer with several questions, several answers. I'll wait a little bit to give a few more people a chance to vote. It's a question with a lot of answers. I want to point you to a little nitpick here. Which of the following are examples of abstract data types? I wonder if I can... It doesn't want to zoom out. Okay, 30-ish people is what we had for the previous questions. So maybe I'll reveal the answers. So strictly speaking, I would say ADT is not an example of an abstract data type because it's just the abbreviation for abstract data types. It's not an example of it, but okay. Not so important. Let me show the answers. Stack is an abstract data type. We'll talk about that in a minute. Deck is a stack and a queue together, so you can use both ends. That's an abstract data type. Maybe not so well known, but occasionally used. Linked list is not an abstract data type, I would say. It's an implementation, so it's a data structure. And the same is true for binary search tree. Sometimes people use this a bit interchangeably with dictionaries, sorted dictionaries that will come below, but I would say it's a data structure. Queue is an abstract data type. Yeah, resizable array is a data structure. That's right. It's not an ADT. Same for heap. Priority queue is an ADT because there's, well, it is according to my definition. And symbol tables, again, that's the abstract data type that is implemented by binary search trees. So that's correct. Okay, cool. I hope we get the terms a little clearer or better separated in a minute. Let's talk about the simplest example maybe of an abstract data type, the stack. And as I said, an abstract data type has to specify the operations that you can do. And what's implicitly behind this is also what is a stack? A stack is a collection of objects. And you can do basically three things with it. You can ask, what is the currently topmost element on a stack? So you can return that item. And top is understood as not modifying the stack. You can push an item onto the stack. So there's a new book entering the stack, and you just put it on top, what we all do. That obviously grows the stack by one item. And you can pop the topmost item off. What you cannot do in a safe way is like take this book out and hope that the rest will not collapse. So a stack does not allow this. It only allows access to the topmost element. It's usually useful to also have a way to check if the stack is empty and to create a stack from scratch if you start with nothing. I guess that's known to you, but just to be on the safe side, let me ask you this little question to see if you understand that part and to make sure you're awake. So you have a stack with numbers, and in the picture I drew, it would be 1 is at the top. And again, I read the numbers top down. So this is top down, and you should do the same for the answer. This is top down, read the numbers on the stack. Okay, I see not everyone has voted, but the result is so clear that I would say you got this, and no need to waste more time on this. So obviously pop does pop, pop, and then you do one push of the 1, so you read this down as 1, 3, 4, 5. All right, that was easy enough. Now let's talk briefly about linked lists. There's different ways how you can implement a stack. It's an abstract data type, and it doesn't say how you implement it. But one typical way of doing it is like this, with a linked list. And for that, let me briefly repeat what a linked list looks like. I assume you have a programming language that allows you to generate objects. And these objects have fields, and one can be a value, and the other can be a pointer. And we will use this pointer. It's a singly linked list that I will create. It's a pointer to another element, so that will be just the next element in the list. So as an example, take the example from before. We had 1, which was at the top. And this has a pointer to a next element, and that was 3. So this points to the next element. And then we had 4 and 5. The beauty about linked lists is there's no requirement as to where these objects are really stored. They could be just arbitrarily scattered around in memory. And this will have a null pointer because it doesn't have a new element. Now that's a singly linked list. It has a beginning and it has an end, and we can traverse it by following the pointers. That's pretty much what a linked list can do. It's a very flexible way of representing a sequence because at any point in time you can insert a new element by inserting a new element inside this pointer, if you like, pointing to the new element and from the new to the previous successor. How do you make a stack out of this? It's fairly simple. You just imagine that you have these boxes stacked on top of each other, and it always points to the next thing below it. And you have one global variable top that points to the topmost element. So you can access that topmost element through this global variable. And you can pop it by just setting top to the successor, and then this is essentially deleted. And you can add a new item by creating a new one here, setting its next pointer, and then rewiring the top pointer to point to this new element. That's how you do a stack based on a singly linked list in like 2 minutes. As most of you will have seen this, this is probably a sufficient level of detail. How good is this implementation? It's actually pretty good for a stack. It does all operations in constant time, and that's worst case constant time. So there's nothing else we could really hope for. And it requires a linear amount of space. To be a little more precise, we need n of these objects, each of which has to store well, the value that we're representing in the stack and a pointer. So we waste a bit of space in that we have n extra pointers. But other than that, the linked stack implementation is as good as we can hope for. Sometimes this requirement of having n extra pointers is too much, and we can think about if we can do away with these extra pointers. And well, yes, we can if we store the items in an array instead. Now that again is also somewhat easy. We have an array, and I just draw it upwards to make it more look like the stack of books that we had before. And we stored the elements here. So we had 5, 4, 3, 1. And we have an additional variable top that tells me what is the index here. So it doesn't really matter where I start with 0, but let's say it's ordered like this. So top would store 3. So I would always know what is the topmost element. And I can push another element in by setting top to 4 and adding this new element, whatever it is. So far, so good. Easy enough. And well, you can do all the other operations. You can figure out how this works. The problem is, what do we do if we want to pop and the array is already used up? Because arrays need a fixed capacity. That's how arrays usually work. That's down to the memory management of operating systems and programming libraries. They allow you to allocate a certain chunk of memory, and that's it. You can't easily make it bigger than that if you need that later. So what you can do is you can either say, let's do a fixed size array and have a fixed capacity for our stack, and we can never ever go above that capacity. Then we need that capacity of space, but there's no extra pointers. This is really just the space for C elements. So that's good. In terms of space, this is efficient as long as C is close to the actual number of elements that we need. And all operations are a constant time again. So that's also great, except that this fixed capacity is a bit of a pain in some applications. If you don't know a good bound on the size, then you're screwed with this.